Welcome back, students. Video number 6 is already uploaded for the valence bond theory. Next video is crystal field theory. That is important also. So I marked the star sign here. That is the important concept here. Definitely question related to the CFT will be there in your competitive exam. So what actually it is? This is a model of electronic structure of transition metal complex that consider how the energy of d orbital of a metal affected by the electric field of the ligand. Okay, so that means the thing is how d orbital metal d orbital is affected by the approaching of ligands. That theory it is. So what its theory? Point number one, it assumes ligands and CMA. It assumes ligand and CMA interaction to be purely ionic. Previously, what we are learning in the valence bond theory, coordination bond, covalent bond, but here they are saying purely ionic because it assumes only ionic interaction. Second point, it assumes ligand and CMA to be point charge or dipole. CFT explain splitting of only d orbital. It will explain the splitting of d orbital. Does not comment on s and p orbital. CFT always give exact value of magnetic moment. It does not give information about hybridization. So these are the points related to the crystal field theory. So points are not important, but you have to check it once. Now we will check splitting in octahedral complex. Splitting in octahedral complex. Octahedral complex. So what happens in octahedral complex, children? In octahedral complex, coordination number in the valence bond theory also we did. Coordination number is 6. And metal ion will be in center and ligand occupy the 6 corner of the coordination 6 corner of the octahedron. Okay, so here I am writing metal ion will be on center and 6 ligand occupy the 6 corner of octahedron. So how they will occupy? Check it once. Here this is the metal. In this metal, these are the 6 corner. Okay, these are the 6 corner. Which type of complex it is? ML6. So d orbital we know. How many d orbital we are having? That also we have to check. 1, 2, 3, 4 and 5. First is called dxy, dyz, dzx, dx square, y square, dz square. These are the orbitals name. So we know that what we know? We know that two orbitals. Which two orbitals? These two orbitals. Dx square, y square and dz square are oriented along the axis. Dx square, y square, dz square oriented along the axis, and remaining three orbitals are oriented in between the axis. Okay, so here that is x-axis, x dash, y-axis, y dash, z-axis, z dash. So two orbital, which two orbital? These two orbital oriented along the axis. Remaining three, what are the remaining? These three in between the axis. So here these two are designated as EG orbital, and remaining dxy, dyz, dzx, they are designated as, named as T2G orbital. So the thing is, as the six ligand approach the metal, six ligand approach the metal along the axis, hence ligand will approach along the axis. Then what happened? So what I said, as the six ligand approach the metal along the axis, EG orbital, this EG orbital is repelled more by the ligand, is repelled more, EG orbital is repelled more as compared to T2G orbital. Why? Because energy of EG orbital increases much more than energy of the T2G, because energy of EG orbital increases much more than T2G. So what happened, children? In octahedral complex, in the octahedral complex, five orbital is split up into two set. How they will split? Suppose this is your d orbital. 1, 2, 3, 4, 5. Okay, so named dxy, dyz, dzx, dx square, y square, dz square. So they will be splitted into two set. One set is your higher energy that I told, Eg. One set lower energy, that is T2G. Here it is dx square, y square, dz, dxy, dyz, dzx. So it is your higher orbital, higher energy, and it is lower energy. Higher energy, previously also I said axial orbital, axial orbital, because these two orbit dxy, dx square, y square, dz square from the axis, and these are non-axial orbital. Okay, so that is the condition. So what is the diagram for this? Let us check it. I'm erasing it actually now. So what happened here? Once again check it. Here d orbital, 1, 2, 3, 4, 5, state 1, and 5d orbital when no ligand. Then 5 degenerated orbital, degenerated orbital with ligand. That is your state 2. Now splitting. What happened? Splitting. So here 3 orbital, state 3, and here 2 orbital. Okay, in that case this gap is represented as delta naught, crystal field splitting energy. What it's called? CSCF, crystal field splitting energy. CFSE, crystal field splitting energy. So from here, this value is 0.6 delta naught, and here this value is minus 0.4 delta naught. This is your T2G, this is your EG. This line is called Barry center. What it's called? Barry center. It's called Barry center. You can count it. Here two orbital, so plus 0.6 into 2, value is 1.2 delta naught. Here minus 0.4 into 3 orbital, then minus 1.2 delta naught. So total splitting, that delta naught is your total splitting. So what is the average? So average is plus 1.2 minus 1.2, that is 0. Okay, so that is the diagram. In the next case, so check it once. This is the very important concept and it will take time also. Here we are having 5d orbital, 1, 2, 3, 4, 5. In that case, we are checking the energy gap. So check it. Here this is delta naught, and here this is delta naught. 3 orbital T2G, 2 orbital EG. Similarly here T2G, here EG. So filling of electron according to Hund's rule. Hund's rule followed. When, what are the conditions? Weak field ligand. Here this side. Weak field ligand, low energy difference. Here less energy difference. Less energy difference. Here strong field ligand, two conditions I showed. In this case weak field ligand. Here in the second case strong field ligand. more energy gave, more energy difference. Okay, so check it once. Crystal field splitting energy. Here I am writing CFSE, crystal field splitting energy for what? Octahedral complex WFL. If weak field ligand is there, then delta naught energy is greater than P. P is what? Pairing energy, and it will be high spin complex. High spin complex follow Hund's rule. P is what? Pairing energy. Pairing energy means the amount of energy required to pair the electron. The amount of energy required to pair the electron, that is called pairing energy. So here crystal field splitting energy is equal to 0.6 into A plus B into minus 0.4 delta naught. Here also delta naught. A means what? Electron in Eg. B means what? Electron in T2G. Okay. Second concept, crystal field splitting energy for SFL, strong field ligand. Here delta naught is greater than P, pairing energy. Low spin complex not follow Hund's rule. That is all about the octahedral complex. Okay. Crystal field stabilization energy 0.6 A, electron in Eg and T2G delta naught. In that case, one more formula is given. Crystal field splitting energy is equal to minus 0.4 into N T2G, means electron in T2G, plus 0.6 into NEG, plus pairing energy, and outside of the bracket delta naught. Now splitting in tetrahedral complex. So what happened here? Tetrahedral splitting is always less than octahedral splitting. Kunz will follow because it is a high spin complex. Here coordination number, tetrahedral means 4, coordination number 4. The tetrahedral arrangement of 4 ligands surrounding a metal ion may be visualized by placing ligand at the alternate corner of a cube. You can, that is metal, that is the cube. Here we are having metal. So what happened here? Ligand, that is x-axis, here y-axis, and here z-axis. Ligand will approach here and ligand will approach here. It will approach here. So 4 ligand will approach, tetrahedral arrangement of ligand. Okay. So what is the concept here? None of the d orbitals point exactly towards the ligand. When ligand approach, it is more close when ligand is approaching, when ligand approach, it is more close it is more close dxy, dyz, dzx in comparison of dx square y square dz square, because dxy, yz, zx are between the axis and dx square y square dz square along the axis. So what is the difference? So these three orbital feel more repulsion as compared to these two. Thus, d orbital also split into two groups. Check it once. Here, d orbital 1, 2, 3, 4, 5. State 1. Then what happened with ligand 1, 2, 3, 4, 5. With ligand state 2. Now dxy dyz getting more repulsion, then these three orbital now this time higher energy level, and these two are lower energy level. This is the state 3. It's called T2. It's called E. Energy gap 0.4 delta naught, delta T actually it's called, and here minus 0.6 delta T. So this is the splitting of tetrahedral complex. So like this, crystal field splitting energy is completed. Question related to the crystal field splitting energy we will complete in the next video. So thank you. Watch the video. It is already 30-minute, more than 30-minute video we have completed. The remaining part is questions related to the CFT and isomerism. So one or two video chapter will be completed.